Hi guys, sound check. Okay, as you can see, there are few of us, but we're desperate for knowledge. So I think it's a good time to start. Okay, let me announce the plan for today. What are we going to do? So first of all, I want to discuss fields, and specifically finite fields. So fields with finitely many elements. There are a lot of them, actually, not only ZP. And later, I will apply finite fields to produce Galois random generator. And after that, I will apply the Galois random generator to string ciphers. I will explain what the string ciphers are and how to apply random generators to them. Okay. But first of all, fields. Suppose F is a field. Then it contains the identity element, the neutral element with respect to multiplication. It's called 1. We can start adding this element, like 1 plus 1 plus and so on, plus 1, n times, where n is a positive integer. Well, it may happen that after several iterations, we will get 0. So, this leads to the notion of a characteristic of a field. So let me define the characteristic of a field as follows, the definition. So F is a field. Then the smallest positive integer, the smallest positive integer p such that 1 plus etc. plus 1 p times equals 0 is called a characteristic of the field F. Of F.
And if field does not have a characteristic, we say that its characteristic is infinitive, or?
What again?
If the field does not have a characteristic, then we say that it's infinitive, or what?
But give me a second. This will be in a second. If there is no such p, we will say that the characteristic is 0, not infinity. And I will explain in a minute why we would like to define it by 0, not by infinity. So if there is no such p, then we say that the characteristic is 0. So we will denote the characteristic by char F, and it's either 0 or p, where p is a positive integer? Well, actually, the characteristic is always a natural number. And we will show in a minute that if the characteristic is not 0, it must be prime. So it's either a prime number or 0. And for convenience, I would like to introduce an additional notation. So instead of writing this 1 + 1 + 1 p times, I will write simply p times 1. Here p is an integer and 1 is an element of the field. So this is an element of the field and p is just a natural number actually. So then the result is a well-defined element of the field F. So this is just a simpler shorthand for this notation. So you just multiply a natural number by an element of a field. So you can actually use this notation for any element of the field, like x plus x plus x, p times equals p times x. So, okay. So now, let me explain the relation between the characteristic. Oh, by the way, let me give you an example, first of all. Example. So if you take F to be Q, which is the field of rational numbers, then the characteristic of Q equals 0 because 1 + 1 + 1, and if you take it any amount of times, it's never 0. And the same happens with the field R and C, the real numbers and complex numbers. On the other hand, if you take ZP as a field, then the characteristic of ZP is P. It's a prime number. So these are the examples. Okay. Next, I want to explain the relation between the characteristic and the ideals in the ring of integers. So the remark, well, suppose F is the field. This is our field. Let's write it like this. F is a field. Z is the ring of integers. Then we have a unique homomorphism from Z to F. There is only one homomorphism from Z to any ring, which takes n to n times 1. Here we use the notation above. So this is the only possible homomorphism as a homomorphism of rings from the ring Z of integer numbers to any other ring. In particular, we can produce a homomorphism from Z to our field. Why it's unique? Well, if we take the element 1, which is the identity element of Z, it must go to the element 1 of the field F by the definition of a homomorphism. But then the element n is just a sum of n identities from Z. So it must go to the sum of n identities of F by the definition of a homomorphism. It must preserve the addition. So this is the only option for this homomorphism. And let me denote it by phi. Then the kernel of phi is an ideal of Z, and we know that any ideal is generated by some natural number. So the ideal generated by P. So which means P times K for K in Z. And what is this P? P is actually the smallest possible integer such that P times 1 equals 0. So just by definition of the kernel, P is smallest. If we take it to be positive, then P is smallest positive integer such that P times 1 equals 0. So this simply means that P is equal to the characteristic of the field F. So if there is no such P, then the kernel is the zero ideal, which means that Z to F is an injective map. And in this case, the generator is equal to zero. So in this case, it coincides with our definition of the zero characteristic. So we want the characteristic to be the generator of the kernel for this specific homomorphism. So if there is no such P that P times 1 equals 0, then we want the characteristic to be 0. Are there any questions regarding this remark? Okay, so let me explain that the characteristic is always prime if it's not 0. So the claim. Suppose F is a field. And suppose that the characteristic is not 0. Then P is prime. Okay. Suppose not. Suppose that P is equal to n times m, where n and m are strictly greater than 1, so they are positive integers. In this case, consider the sum 1 plus 1 P times. Well, reorganizing the order of these elements, we can group them up into blocks of n elements, and there are exactly m blocks. So if you just consider the expression on the right and you expand the bracket, this expression, you will see that on the right hand side there are exactly P elements. So the left hand side and the right hand side are the same. But by definition, the left hand side is equal to 0 because P was the characteristic, so this sum must be 0, and P was the smallest possible number. Since n and m are strictly smaller than P, this element is not 0, and this element is not 0 because n is strictly smaller than P and m is strictly smaller than P. Why? Because m and n are strictly greater than 1, so because of this equality, they must be strictly smaller than P. So in this particular case, we see that n times 1 times m times 1 equals 0, but the first factor is not 0, and the second factor is not 0. So these elements are 0 divisors. But 0 divisors are not invertible. So are not invertible. This contradicts to the fact that every non-zero element of a field is invertible. So that's it. So that's the reason why the characteristic of a field must be prime.
Excuse me,
Okay.
is it necessary to get this particular contradiction? Because previously we have that 0 times 0 is not equal to 0. Ah, okay, there might be such a situation. Okay, sorry.
Okay. So there is no question.
Yeah.
Okay.
Excuse
So
me.
now, yep.
Can I ask a little question? I mean, just are we not considering the field of like the group like ZP, where you said the P is this checker of the group? I mean, shouldn't it always be prime or not prime?
Oh,
For example,
mean,
if we have the field of ZP, where P is, I know, 10, but it's not prime. So.
But Z10 is not a field.
Oh, okay. So, okay. Got
So
it.
here we extensively use the assumption that F is a field.
Mm-hmm. Okay. So I missed that Z10 is not a field. Sorry. Thank
So
you.
ZP is a field if and only if P is a prime number.
Mm-hmm. Okay. Okay.
Mm-hmm. No problem. Well, we can weaken this condition actually a bit in order to prove that the characteristic is prime, but I don't want to go into full generality. It doesn't make any sense. Okay, so the next thing I would like to discuss is I want to discuss fields of prime characteristic. And actually, if you have a field of a prime characteristic, you can find ZP inside this field. That's an interesting thing. So the claim, well, suppose F is a field and it has a prime characteristic. Then F contains ZP as a subfield. So F contains ZP as a subfield. Well, if it's not completely clear what it means, you will see in a minute what I'm going to prove. Okay, so let me consider these the element 1 in the field F. Then I want to produce this series of elements: 0, 1, 2 times 1, 3 times 1, etc. P minus 1 times 1. Here, the first factor is an integer, and the second factor is the identity element of the field. Well, and this is just the 0 element. So this is just a subset. So let me denote this subset by E, and E is a subset of F. But now let's try to add and multiply these elements. We will see that the subset is closed under addition and multiplication, and it actually behaves exactly as ZP. So what I'm going to show that if you take a map ZP to F, taking each remainder n to the element n times 1, well, you will get a map from ZP. Well, you will get a bijection, obviously, from ZP to E. And I would like to show that this bijection is actually a ring homomorphism, and actually a ring, which means that it will be a ring isomorphism. So this is what I want to show.
Can I ask?
Yeah.
Can you, after the proof, give an example of a field that is not entirely isomorphic to ZP, but it has a finite characteristic, not finite, non-zero characteristic?
Okay, I'll show it on the, in a minute after I prove this result.
Yeah,
because,
sure.
well, I need to discuss the technique how to produce a field, but this will be a starting point. So what I'm going to explain that every field of prime characteristic contains ZP. So you may consider it as an extension of ZP. And then if we want to produce a field of a prime characteristic, we just need to start from ZP and extend it in some way. And we actually already know the machinery to produce a larger field if we are given a smaller field. And I will show you how it works. But let me complete the proof of this statement. So now we want to show that this ring actually, well, I mean, we want to show that this subset E is actually a ring, and this ring is isomorphic to ZP under this bijection. Well, in order to prove that, we actually need to show that n times 1 plus m times 1 is equal to n plus m modular p times 1 and n times 1 times m times 1 equals n times m modular p times 1. So if we show that these equalities hold, then well, this means that these, well, first of all, this will mean that E is closed under addition and multiplication, so it's a subring. And second, it means that the map from ZP to E preserve addition and multiplication, and it's clear that it preserves the identity element. So this is all we need to prove. So I will show the first one. The second one will be exactly the same. So suppose that n plus m equals q times p plus r, which means that r is the remainder when we divide n plus m by p. So and we want, so this expression is actually r. So this expression is equal to r. So we want to show that n times 1 plus m times 1 equals r times 1. Okay, but we know that n times 1 plus m times 1 equals n plus m times 1. Then we replace n plus m by this expression, q times p plus r times 1. Then we use distributivity law again, q times p times 1 plus r times 1. But here, in this case, we can rewrite it as q times p times 1. And by the definition of the characteristic, this product is 0. So the whole sum is 0. And thus, it is equal to r times 1. So this is the required equality. We wanted to prove this, and we get this, exactly what we needed. So in the second case, we do exactly the same thing, but we put dot here instead of plus, and it works exactly the same. Well, the beginning is a bit different, but I think it's a good exercise. Okay, so let me summarize what's going on here. So if you have a field of prime characteristic, you can take the element 1, you consider all its integer multiples, so you just add 1, then 1 plus 1, 1 plus 1 plus 1, etc. When you take p minus 1 times the sum, it's not 0 yet, but if you take p, the sum p times, you will get 0, and then if you take p plus 1 times the sum, you will get 1 again, and so on. So if you add 1, you will you will get the same elements, or you will get this set. Okay, and this set is actually a subfield isomorphic to the P. And the isomorphism is obvious. You just take 0 to 0, 1 to 1, 2 to 2 times 1, 3 to 3 times 1, etc. That's how it works. Okay, are there any questions regarding this proof? Okay, so now I want to discuss extensions of fields. So, field extensions. Okay, so if we have a pair of fields, K and F, and K is a subfield of F. So here K is a subfield. Then we will say that F is an extension of K. F is an extension. In this case, we may consider F as a vector space over K.
Do you request F to be a field?
Yeah, F, both of them are fields. F and K are fields. But for this fact, it doesn't matter. But I just want to consider fields only. I just don't want to bother with more general rings. Okay, so in this case, F is a vector space. So why? Well, just by definition, what does it mean that you have a vector space? It means that you have a set. You can add the elements of this set, and you can multiply these elements by the elements of the field. But okay, F is already a field. It means that you can add the elements of F, and you can multiply any element of F by any element of F. But K is a subfield of F, so you can multiply any element of F by the element of K, by any element of K, since K is a subset of F. So just by definition, well, you have to check the axioms, but these axioms follows from the axioms of the field. So F is a vector space over K. In particular, there is a notion of a dimension. So, and in case of fields, it has a specific notation. We will denote the dimension of F over K by this symbol. Here is semicolon, F semicolon K, and it's just the dimension of F over K, consider it as a vector space. And the example we know, if we take R, it's a subfield of C of complex numbers, and we know that the complex numbers considered as a vector space over R has bases like 1 and I over R. So C is a two-dimensional vector space over R. So it means that using this notation, we have this. And we usually call this the degree of F over K. Degree of F over K. Well, that's not important. Well, this is just a terminology, but just in case for you to know what it means when people talk about a degree of a field over another field. It's just a dimension of a larger field considered as a vector space over smaller field. Okay, so now I want to discuss a way to produce a larger field using a smaller field. So how would we do that? Well, suppose we have a field K. Oh, by the way, I will call it an extension by a root. By a root. So suppose we're given a field K. It's a field. And we want, oh, and by the way, and we have a polynomial F with coefficients in K. And what I want to produce, so what I want to produce a field L containing K as a subfield. So this is a field. And an element alpha of L, such that alpha is a root of F. So I want to find probably a larger field with an element being a root of a given polynomial F. So if K already contains a root, there is nothing to do. But suppose F doesn't have a root in a field K. So how do we produce a larger field containing a root? So this is the question I want to address now. So as we know, the polynomial F can be expressed as a product of irreducible polynomials. So if I solve this problem, for example, for P1, and I find a larger field with a root for P1, then will this L, together with this alpha, solve the same problem for F. So if alpha is a root for P1, it's a root for the whole polynomial F. So in order to find such a field, we can replace f by p1, and we may consider the case where f is just a reducible polynomial. So from now, so we may assume that f is irreducible. So now the problem is how to produce a larger field where an irreducible polynomial has a root. So let me define L to be the remainder ring K of X quotient by F. As we know, this ring is the field if and only if F is an irreducible polynomial. So since F here is irreducible, this is a field. Now I want to find an element alpha here. Well, I'll denote by alpha the element X of this field. Well, just let me recall, just by definition, here are, what is here? Here are the sums of the form a1, a0, a1x plus etc. plus a n minus 1 x to the n minus 1, where a I are the elements of K and n is the degree of F. So we consider all polynomials of degree strictly smaller than the degree of F. So here we can, the element X lives here. So I will denote by alpha the element X inside this set. So now I want to show that this alpha is a root of the polynomial f. Okay, but what should I do? I should take f of alpha, I should compute f of alpha in L. Well, what does it mean to compute f of alpha in L? Alpha is just x, so I just want to compute f of x in L. But how do I compute an element in L? I just consider its modular f, but f of x equals 0 modular f, which means f of alpha equals 0 in L, and that's it. So this ring is a field, and the element x in this field is a root of the polynomial f. So this is the way to produce a field if you're given another field and an irreducible polynomial. Are there any questions regarding this procedure? Okay, so probably, yeah, let me show you an example. So how did we define a field of complex numbers? So we started with the field R of the real numbers, and we were given a polynomial x squared plus 1. Well, this is a polynomial here. It doesn't have a root in R, so there are no roots here. And this is an irreducible polynomial. Then, if we consider Rx quotient by f, then by definition, it consists of elements a plus bx, where a and b are here. And okay, how do we add and multiply the elements here? Well, we add them just coefficient-wise. And how do we multiply? We consider a plus bx times c plus dx and take it modular x squared plus 1. But taking the result modular x squared plus 1 simply means that we substitute x squared by the element minus 1, which means that in this ring we have this equality, x squared equals minus 1. But now you see, if you just replace the symbol x by the symbol I, so if you replace x by I, you will get exactly the definition of the complex numbers you've seen during the course of linear algebra or calculus or any other course. So just by definition, the field of complex numbers is produced using this exact procedure. Okay, and we will use the same procedure to produce a finite field starting with ZP here instead of R. I will see this in a minute, but before discussing specific examples, I want to discuss some general facts about finite fields. Okay, so finite fields. Okay, finite fields. Finite fields. Okay, the claim number one, it's more of a remark than a claim. Suppose F is a finite field. Well, F is a field and F is finite. Well, then the characteristic of F is not zero, and it's automatically prime. And as a consequence, F contains ZP as a subfield. So any finite field has a prime characteristic, and it contains ZP, where P is its characteristic, as a subfield. Well, it's more or less obvious, modular the results I already proved, but let me prove it for completeness. So, well, why the characteristic is not zero? Well, you can explain it like that, like this. Just consider this homomorphism from Z to F, taking n to the element n times 1. But Z is infinite and F is finite. So this homomorphism is not injective. So the kernel of the homomorphism is not zero. But the kernel is generated by the characteristic. So it means that the characteristic is not zero. That's it. Well, you can do it directly using the definition, but I just wanted to demonstrate this approach. Are there any questions regarding this? Okay, and the second part is automatically follows from the previous statement, where we prove that if the characteristic is prime, then our field contains ZP as a subfield. So this is just a direct corollary of the previous claim. Yep, there is a question? Oh, okay. Now, the next thing I want to discuss is how many elements are there in a finite field. So the claim is this. Suppose F is a field and it's finite. Well, suppose its characteristic is P, then it contains exactly P to the n elements, where n is its dimension over ZP. So again, if you have a finite field of a prime characteristic P, it contains ZP. So it's a vector space over ZP. So we compute its dimension. It's this number n. Then the amount of elements of F must be P to the n, where P is the characteristic and n is this dimension. This is the claim. So for example, there is no field containing 6 elements because 6 is not a power of prime number. Only powers of prime numbers are possible here. So why is that? Well, from the previous claim, we know that ZP is a subfield of F. So F is a vector space over ZP. Well, it's a finite set. So since it's a finite set, it must be a finite dimensional vector space. So since F is finite, so the dimension of F over ZP is also finite. So every basis is finite because there are only finitely many elements. So let me denote the dimension by n. So this is the dimension. But if you have a finite dimensional vector space and you choose a basis, then it simply means that as a vector space, F is isomorphic to ZP to the n. This is an isomorphism of vector spaces. So the amount of elements here is exactly the same as the amount of elements here. But here you have p to the n elements. And that's it.
Again, how do you prove it?
This fact?
Oh, yeah.
Oh, okay, let me clarify. Well, actually,
I see. No problem.
so just in case, if E1, En is a basis, then the isomorphism is given by the formula. Here you have a column A1, An consisting of n elements from ZP. Then this column goes to the linear combination A1, E1 plus and so on, An, En. So this is how this isomorphism works. I hope you know this from the linear algebra course. So simply you have like p possibilities for each coefficient, then you have p times p times p and times options for all possible elements of the field. Okay, this is the second claim. Now I want to prove another claim. I want to describe the group of invertible elements of a finite field. Well, there is a miracle. This group is always cyclic. Well, suppose F is a field and it's finite. Then F star is cyclic. Well, this is a miracle, actually. And it's very useful one. Okay, so how do we prove this? Well, first of all, F star is a finite abelian group. Well, then we know that it must be isomorphic to a group of the form like this, D1 times etc. dr, where the numbers where D1 divides D2, divides etc., divides dr. So that was a classification statement about finite abelian groups. Every finite abelian group is uniquely presented in this form. Okay? And in particular, if you take any element x from F star, then x to dr equals 1. Well, because on the right-hand side, if you take any element y, then dr times y equals 0. So on the left-hand side, we have a multiplicative notation. So I raise to a power, and the neutral element is 1. On the right-hand side, I have an additive notation. So rising to a power corresponds to multiplying by an integer, and the neutral element is 0. So it's because of this assumption, we have this. So, are there any questions?
Could you explain one more time why the product is equal to 0?
Oh, why the product is equal to 0? Okay, you see here you have ZD1. If you multiply any element well, y, what is y? Y is a sequence. So element of this product is a sequence y1, etc., yr. This is your y. Okay. If you multiply the element y by some natural number, you just multiply it coordinate-wise. Okay. And y1 is an element here. So if you multiply y1 by d1, you just get 0 by definition. But d1 divides dr. So dr is just d1 times something. If you multiply y1 by dr, you multiply it by d1 times something. So you will get 0 automatically.
Okay.
And it works exactly the same for all other coordinates. Okay?
Okay, yeah, thanks.
So this is how I use this assumption that d1 divides d2 divides d3. So now we see that if x is an element of f star, and we have this isomorphism, then x to the power dr equals 1. But this simply means that if I consider a polynomial ft, which is t to the dr minus 1, then all elements of f star are the roots of this polynomial. So f star consists of the roots of this polynomial. But we know that each polynomial has at most, let me rephrase it. Well, this polynomial has at most dr roots. This is because of the unique factorization property. So if a polynomial has a root, it means that it has a factor of the form x minus alpha. So let me write it here. So alpha is a root of f if and only if x minus alpha divides f. But there are at most degree f linear factors of a polynomial. So there is the amount of roots is not greater than the degree of f. So the amount of roots is not greater than the degree of f. And here the degree is d to the r. So because of this remark, the amount of f star is not greater than dr. Are there any questions regarding this part of the proof? Okay, but from the other hand, we know that f star is this product. So the amount of elements of f star is equal to amount of elements of this group. But how many elements are here? You just multiply d1 by d2 by d3, etc. by dr. So from the isomorphism above, we get that f star contains d1 times d2 times etc. times dr elements. And because of this, it must be not greater than dr. Well, the only possible case for this to happen is if this is equal to 1. So simply means d1 is equal to 1, etc. dr minus 1 is equal to 1. But this means that there is no so what is z1? Z1 is just 0. I mean, you may think of this like d1 must be strictly greater than 1. Otherwise, d1 is just zero group. So it means that there is no factors here. So because of this, f star is just f star is just z dr R, and this is cyclic. And that's it. Should I repeat the end of the proof, or is it clear? Okay, that's good. So, so the multiplicative group of a finite field is always cyclic.
Sorry, can I? If you consider, if we take like some ring R, then R star is just R without all its without zero and all its zero divisors.
Yeah, R star is the set of no. The R star is the set of invertible elements, but in case of a field, only zero is not invertible, so F star is the set of all non-zero elements here.
Okay, thanks.
No problem. Okay, so now I want to formulate a claim without proof. Well, let me see. Okay, yeah, I just want to explain how any finite field looks like. So, well, from the claims above, we know that every finite field of characteristic P contains ZP as a subfield, and it must be of P to the n elements. It must contain exactly P to the n. It must contain exactly P to the n elements. So, but how many fields do we have for a given number n? So, the claim says that for each prime number P and each natural number n, if you have exactly one finite field consisting of P to the n elements, uniqueness here is up to isomorphism. So suppose that P is prime and n is a positive integer. Then there exists a unique up to isomorphism field F containing exactly P to the n elements, such that it contains P to the n. So you can always produce a field with P to the n elements, and no matter how you produce this field, all these fields are isomorphic. So it doesn't matter how to produce a field with P to the n elements, because the result will be exactly the same. Okay, so let me discuss, well, the structure of finite fields using the results we already know. Okay, so again, the starting point for any finite field is the field ZP. Oh, by the way, since there is only one field containing P to the n elements, it has a name. So the field of P to the n elements is denoted by this. This is the field of P to the n elements. So since it's unique, we may give him a name. In particular, FP is just another name for ZP. So usually when people discuss finite fields, they use FP instead of ZP. But I will try to stick to this more convenient notation. Probably it's more convenient to you. Okay. But now, how do we produce all other finite fields? Well, but one important remark. Fp to the n is not isomorphic to Zp to the n. So this is a common mistake, but that's why I want to clarify that this finite field is not the same thing as this ring. Why? Well, we know the right-hand side contains zero divisors, So here, for example, if you take element p, then p is not 0, but p to the n is 0. It's nilpotent, but it's not invertible. So this is not a field. If n is greater than 1. Because, I mean, if n is equal to 1, then p is equal to 0. So here in this assumption, I assume that n is greater than 1. So if n is greater than 1, then p is not equal to 0, but p to the n is equal to 0. So this guy is not a field if n is strictly greater than 1. Yeah, let me add this here also. So if n is strictly greater than 1. So how do we produce a finite field? So yes, now I'm answering to the question from the beginning of the lecture. So, well, you start from ZP, and then you must take an irreducible polynomial of degree n. So this is an irreducible polynomial of degree n. Well, this is a painful procedure, but there is an algorithm how to find irreducible polynomials over a finite field. We discussed them during the previous seminar, but okay, nevertheless, it's an unpleasant procedure, but you can find an irreducible polynomial of degree n, and then you can produce fp to the n as a quotient. So you take this ring of the reminders, zpx quotient by f, and this is your finite field. By the way, it may happen that there are many irreducible polynomials of a given degree. So for example, you have f1, f2, f3, and so on. And each irreducible polynomial will give you this finite field. And no matter which polynomial you take, the result will be exactly the same up to isomorphism. So, for example, if you take, let me say, if you take z5, the polynomials x squared plus 2, and with my list of reducible polynomials, and another is x squared plus x plus 2. These are irreducible polynomials. They are polynomials of z5x, and they are irreducible. So from one hand side, you may produce z20 or f25 as z5x modulo x squared plus 2, or you can produce it as z5, let me write y, modular y squared plus y plus 2. So these are exactly the same set, but with different multiplication. But still, you can find an isomorphism, which takes some element from here and maps it to an element here. We will discuss how to find such an isomorphism during a seminar session. But I just want to clarify that it's always possible to find such an isomorphism, because the resulting field must be unique up to isomorphism. So how do you choose which polynomial to take here? Well, you just take the one you think is better for your particular purpose. So if you think that this polynomial is easier or better to use for some reason, just use this one. If you think that this one is not suitable, then just replace it by this one or any other polynomial. There are actually 10 irreducible polynomials of degree 2 over z5. So all these polynomials give you exactly the same field. Yeah. Another example is this. So if you take, say, z2, there is only one irreducible polynomial of degree 2, and then f4 can be constructed uniquely. And let me describe its elements explicitly. So the elements of F4 are just these polynomials, a plus bx, where a and b are elements of Z2. So there are only 4 elements, well, like the number 4 here. And how do you multiply them? Well, and how do you add them? Well, the addition is coefficient-wise. So if you have a plus bx and c plus dx, you just add a. So if you have these guys, so you just add a and c and b and d as an elements of Z2. So the addition is simple. And in order to compute the product of these 2 elements, you actually just need to know the product of all possible power, the products of all possible powers. So you just want to multiply 1 and 1, 1 and x with and x. So this is simple, just by definition of the identity. But x times x is x squared. But here in this field, we know that x squared plus x plus 1 is equal to 0. And since we're in Z2, this means that x squared equals x plus 1. So this is x plus 1. And we can express this as a multiplication table. So we multiply here 1 and x, 1 and x, and we fill the table as follows. So this is the multiplication table for the field F4. And using this multiplication table, you can compute explicitly the product of these 2 elements. So you just do it in the same manner you deal with the complex numbers. So in case of complex numbers, how do you multiply these expressions? Well, you multiply these guys in the usual way, but when you meet I squared, in this case, it will be x squared. You just replace it by this expression. So, but everything is exactly similar to the case of complex numbers. Okay, and another remark I want to give, it will be remark 4 probably, I don't remember exactly the name, the number. So when we discussed cryptography, we used this group because the discrete logarithm problem is hard to solve here. But ZP is a subfield of Fp to the n for any n. In particular, the invertible elements form a subgroup here. And if it's hard to solve the discrete logarithm problem here, then it's hard to solve in a larger group. Well, why? Because if it were simple to solve an equation like g to the x equals h, we'll solve for x. If it were simple to solve this equation here, then just take g and h to be elements of this subgroup, then it would be simple to solve this equation here. But we know that it's hard to solve this equation here. So if it's hard here, then it's hard in a larger group. And the right-hand side is also a cyclic group, as we know. So in any, so we can use FPN star in cryptography using Diffie-Hellman approach. So this is one option how to exploit finite fields in cryptography. So you just produce this field. You find it's the generator of the group of invertible elements, and then it's a cyclic group, and you use it in the same way. In the same way, you use ZP star in the Diffie-Hellman approach. Okay, but there is one additional remark. Well, how do we find a generator of the multiplicative group? Well, somehow you have to guess which element is a generator. And if you produce a field in this form, in this way, then a good candidate would be the element X. Well, but it turns out that the element X is not necessarily a generator for the multiplicative group. And the example here with the field Z5 actually is a good example because, well, if we produce our field F25 as this, then the element X is not a generator. But if we produce our field F25 as this, then the element Y is a generator. So sometimes the reason why you prefer this one over this one is because in this case, this element is a generator of the multiplicative group. Oh, by the way, that's not what should be written here, F25 star. The group is the set of all non-zero elements. So in this case, so the reason why you prefer this, because here the element Y itself is a generator of the multiplicative group, and here the element X is not a generator of the multiplicative group. Let me write it here of F25 star. That's an important remark. So yeah, in this case, the generator must be something like X plus 1, or you just find an explicit expression for the generator. So it's harder to deal with the generator here than here. Okay, now I want to present the Golar random generator. I don't have much time, so let me switch to the Golar random generator. So what is the Golar random generator? Well, there is a notion of a linear feedback shift register. It's just a scheme to generate random numbers, and it's usually presented in two forms: Fibonacci form and Galois form. I will discuss the Galois form because it's because it's related to finite fields. It's a bit more complicated than the Fibonacci form, so it makes sense to discuss it. And actually, they are dual to each other, but I don't want to bother with this. So how do you generate random numbers? So suppose you have a finite alphabet, and as a finite alphabet, I'll take the elements of ZP. Then what is a word of length n? A word of length n in this alphabet is just ZP to the n. So this is just a sequence of elements of ZP. Now, the goal is to produce a random element of this set. How to randomly choose an element of here. And actually, I want to produce a sequence of random elements from this set. Well, here is the plan. You take Fp to the n. You produce it as a quotient ring, Zp of x, quotient by f, where f is an irreducible polynomial of Zpx of degree n. So then you identify this set with the set of polynomials of degree strictly smaller than n. So each polynomial is uniquely determined by the sequence of coefficients. So now the question is how to randomly choose an element of the finite sphere, or how to generate a sequence of random elements from a finite sphere. So you first you find a generator of the multiplicative group, and then you just consider the powers, all possible powers of the generator. Then each power corresponds to a polynomial of this form, and each polynomial of this form gives you a sequence of coefficients, which gives you a random sequence of length n. This is how it works, and that's it. So you just can. Yes? There was a question. Could you repeat?
Can you repeat the explanation?
Oh, okay. So let me show you the whole picture. So you take ZP, you find an irreducible polynomial. Let me write it. Irreducible polynomial of degree n over ZP, and you construct this finite field as this quotient ring, ZPX modular F. Well, explicitly, this ring of reminders consists of these elements. These are just polynomials of degree strictly smaller than n, with coefficients in ZP, and they are in one-to-one correspondence with the sequences of length n. Then you choose a generator of the multiplicative group of Fp to the n. And now, how to generate a sequence of random elements of Zp to the n star? Well, you just consider the sequence of all possible powers of your generator. And each generator, each power corresponds to a polynomial of the form a0, let's say 3 plus a1 3x plus etc. plus an minus 1 3x to the power of n minus 1. So here it's just an index, it's an upper index. So you just take g, well, it's also represented in such a form. You raise it to the power 3, then it corresponds to a polynomial of this form, and the sequence of coefficients gives you the required random sequence on the step 3. So, and then this process gives you a sequence of sequences of the length n. This is how it works. Is it clear now?
Yep.
Okay, well, you can modify this process a bit. Instead of starting from the power 1, you can start from the power k. So you just choose random k, like any k fixed, and just generate a sequence like this. In practice, instead of choosing a power k, people usually take just an arbitrary non-zero element h of Fp to the n and consider sequence like h, then h times g to the square, etc. Well, because h is not 0, it's an element of Fp to the n star, so h is represented as a power of g, so this sequence is exactly the same sequence as this one, but you don't choose this power k explicitly. You just encode this this choice in the choice of the element h from this subfield. The h must be non-zero. That's the only restriction here. So this is how the Galois random generator works. You just consider this sequence, and this gives you a random sequence of sequences of the length n. Okay. Well, I'll skip the matrix form for the seminar session. Let me discuss stream ciphers. I have like 5 minutes for doing that. Stream cipher. So in this case, you have an alphabet consisting of 2 elements, 0 and 1. And so what you want to do is this. So you have a sequence of elements, which is your message, A0, A1, A2, A3, etc. And you want to transfer this message via an open channel. Well, usually you have a secure channel and an open channel, and it's very expensive to broadcast something via the secure channel. Well, it's not necessarily expensive in terms of money, but it could be expensive in terms of computation, because you have to do a lot of computation in order to encrypt and decrypt your messages. So you want to utilize open channel as much as you can. But it's not a good idea to send not encrypted message through an open channel. So the way you can encrypt it is very simple. You can generate a random sequence. Here it must be random, S0, S1, S2, S3. And instead of sending the initial sequence, you consider the sum modulo 2 of these elements, and the result will be D1, D2, D0, D1, D2, D3, and you send this sequence instead. Then, if you want to decrypt the message, you must know the whole sequence S0, S1, S2, S3. Well, you could transfer the sequence via secure channel, but well, it's not better than transferring the initial sequence via the secure channel. So instead of transferring this thing, you do the following trick. Well, you just take your random generator. Oops. You just take your random generator. This is your random generator, and you send the random generator via the secure channel. Now you and another guy, you both have the same random generator, and the procedure of communication looks like this. So you have the random generator, and the other one has the random generator, and they are synchronized. Then you have this. If you want to send an element AK, so suppose you're on the kth step, you generate the kth random number, you feed these elements to the XOR block. It computes the sum modulo 2 of these elements. Then, when you want to decrypt this message, you generate kth random number and you add it to the element you received, and the output will be initial AK element. So here you just need to use two synchronized random generators, and you pass the copy of your random generator via the secure channel, and then you can use the open channel using this. And this procedure is very cheap to compute. The hardware can do this, and actually GSM standard uses a little bit more enhanced version of this approach. Uses this idea. Well, they actually use free random generators. They communicate to each other in some complicated fashion, and then you encrypt this message using free random generators, and you use one random generator only for sequences of a specific length. It's probably 113 symbols only, and then you just choose a different random generator, and so on and so on. So GSM standard, you may Google something like A5 algorithm. A5, there are A5.1, A5.2, and A5.3 different versions of this algorithm. So if you Google this, you will find a complete description how it works. So yes, this is a state-of-the-art approach. I mean, not exactly this one, but if you just tune it a little bit, then you will get a state-of-the-art approach, which is used in mobile phones. Okay, so this is a string cipher. And how do you apply the Galois generator here, by the way? So here you need some some random generator here, and you usually use the Galois random generator here. Yeah, and by the way, the Galois random generator is not the best possible generator because it's linear, but there are very cool random generators based on the Galois random generator. There is a professor in Denmark Technological University, Agner Fogh. His website is agner.org, and well, he wrote a Bible on optimization on x86 architecture, so he is very famous for doing that. And you can find an article about random generators on his website, and he explains different aspects of random generators, how to write them, what are the state-of-the-art approaches, well, how to use them, which generator is good for doing what. So if you're interested in random generators and how to apply them to security, I recommend looking here. Okay, so we're running out of time. If you have any questions, please ask. If there are no questions, then thank you for being here. Okay, if there are no questions, then thank you. And
Thank you
I'll
very
see you
much.
next time.
Goodbye.
Thank you.